Welcome! In this session, we'll tackle LeetCode problem number 941, Valid Mountain Array. This problem challenges us to identify whether a given array exhibits a specific mountain-like structure. It's a great opportunity to enhance our problem-solving skills and reinforce our understanding of array traversal techniques. Let's dive in and break it down step by step. A mountain array is defined by two key properties. First, the array must have a length of at least 3. Second, it must follow a specific structure. There exists an index I such that all elements before I form a strictly increasing sequence, and all elements after I form a strictly decreasing sequence. This index I represents the peak of the mountain, and it cannot be the first or last element of the array, ensuring there is both an uphill and a downhill slope. Given an array ARR, our task is to determine if it satisfies these conditions and return true if it does, or false otherwise. The input to the problem is a single integer array, and the output is a Boolean value indicating whether the array forms a valid mountain or not. In the first example, we are given an array ARR with the values 2, 1. The output is false because the array does not have enough elements to meet the minimum length requirement of 3. Without at least 3 elements, it's impossible to have both an increasing and a decreasing sequence. In the second example, the input array is 3, 5, 5. Again, the output is false. While the array initially increases, the two equal values at the peak, 5 and 5, violate the condition that the sequence must be strictly increasing and strictly decreasing. A valid mountain array cannot have any flat sections. In the third example, we have the array 0, 3, 2, 1. This time, the output is true because the array satisfies all the conditions of a mountain array. It starts with a strictly increasing sequence, where 0 is less than 3, and then transitions into a strictly decreasing sequence, where 3 is greater than 2 and 2 is greater than 1. The peak, 3, is at index 1, which is neither the first nor the last element. These properties confirm that the array forms a valid mountain. Additionally, it's worth noting that this problem includes constraints such as the array length being between 1 and 10,000, and all elements being non-negative integers up to 10,000. There are several edge cases to keep in mind when evaluating if an array is a valid mountain. First, arrays with fewer than 3 elements, like 1, or 2, 3, are automatically invalid since they cannot form both an increasing and a decreasing slope. Second, arrays with flat sections, such as 3, 3, 3, or 1, 1, 2, 1, 1, are also invalid because the sequences are not strictly monotonic. Third, arrays that only increase, like 1, 2, 3, 4, or only decrease, like 4, 3, 2, 1, fail to form a peak altogether. Finally, arrays where the peak is at the boundaries, such as 5, 4, 3, or 1, 2, 3, are invalid because a valid mountain requires both an uphill and downhill slope with the peak strictly between the two. These scenarios ensure that we carefully verify the given conditions for a mountain array. To solve the problem of determining if a given array is a valid mountain array, we need to ensure that the array strictly increases to a peak and then strictly decreases, with the peak not being at either end of the array. One straightforward approach is the brute force method. Here, we would first locate the peak element, which is the largest value in the array. Then, we verify two critical conditions: that all elements before the peak are in strictly increasing order, and that all elements after the peak are in strictly decreasing order. The steps for this approach involve scanning the array to find the peak index, followed by 2 additional passes, one to check the left section for increasing order, and the other to check the right section for decreasing order. While this method runs in O(n) time due to the multiple passes, it is simple to understand and implement. The brute force approach has a space complexity of O(1) because it does not require additional data structures. However, a key drawback is that it involves multiple scans of the array, which can make it inefficient in practice. To address this, we consider an optimized strategy using a two-pointer approach. This method eliminates the need to explicitly find the peak and verify the sequences separately. Instead, we use 2 pointers, one starting from the beginning of the array and the other from the end. The left pointer moves forward as long as the array values are strictly increasing, effectively simulating the climb to the peak. Similarly, the right pointer moves backward as long as the values are strictly decreasing, simulating the descent. By doing so, we ensure that both the climb and descent are checked in a single traversal. At the end, we confirm that the pointers meet at the same index, which represents the peak, and that this peak is not at the start or the end of the array. This approach also runs in O(n) time since each pointer traverses the array only once. The two-pointer approach is equally space-efficient, with a space complexity of O(1), as no additional data structures are used. However, it does have a drawback in that it can be slightly harder to understand and implement compared to the brute force method, especially for those new to the concept. Despite this, the two-pointer approach is the chosen strategy due to its efficiency and elegance. By avoiding redundant scans and solving the problem in a single traversal, it minimizes runtime overhead. The key insight here is that the peak index divides the array into two distinct sections, strictly increasing and strictly decreasing. By leveraging the two pointers, we can identify this peak indirectly without needing to explicitly find it. The critical observation is that the pointers must meet at the peak for the array to satisfy the mountain array conditions. When comparing the two approaches, the brute force method is easier to implement and grasp, but it suffers from redundant passes over the array, which can be inefficient for larger inputs. On the other hand, the two-pointer approach is optimized for performance, as it achieves the same result in a single traversal with constant space. However, it might require a bit more effort to understand and implement. Considering the constraints and requirements of the problem, the two-pointer approach strikes the right balance between clarity and efficiency, making it the most suitable choice. It ensures that we meet the problem's demands in the most optimal way while maintaining a clear logical structure. In this problem, we aim to determine whether a given array of integers forms a valid mountain array. A valid mountain array has a specific structure. First, it must have at least 3 elements. Anything shorter is immediately invalid. Second, the elements strictly increase from the start up to a single peak, which is the highest point in the array. After the peak, the elements then strictly decrease. Importantly, the peak cannot be at the very beginning or the very end of the array, it must be somewhere in the middle. Our goal is to write an algorithm that takes an array as input and outputs a Boolean value indicating whether the array satisfies these conditions. To achieve this, we'll break the problem down into a series of steps. First, we will check if the array has the minimum required length. Then, we'll identify the peak by traversing the array in the upward direction. Once we find the peak, we'll ensure its position is valid. Finally, we'll verify the downward slope to confirm if the array descends properly after the peak. If all these conditions are met, the array is a valid mountain, otherwise, it's not. Now, let's walk through the algorithm in more detail. After confirming that the array meets the minimum length requirement of 3 elements, we begin searching for the peak. To do this, we initialize an index variable, I, to 0 and start traversing the array. As long as the current element is smaller than the next element, we keep incrementing I. This process stops when the slope flattens or turns downward, meaning the current element is no longer less than the next one. At this point, we've identified the peak location. Next, we validate the position of the peak. If I is still 0, it means the peak is at the very start of the array, which is invalid. Similarly, if I has reached the last index, the peak is at the end, which is also invalid. In either of these cases, we can immediately return false. If the peak is valid, we move on to verifying the downward slope. From the peak onward, we continue traversing the array, this time checking that each element is strictly greater than the one that follows. If we encounter an element that violates this condition, or if we reach the end of the array prematurely, the array is not a valid mountain. Finally, if we successfully traverse the entire array after the peak, the mountain structure is confirmed, and we return true. The efficiency of this algorithm is worth noting. By design, we traverse the array only twice, once to find the peak and once to verify the downward slope. This ensures a linear time complexity, or O(n), where n is the length of the array. Additionally, the algorithm uses a single index variable, I, to track our position, which means it operates with O(1) space complexity. These characteristics make the solution both time-efficient and space-efficient. When implementing this approach, it's also important to consider edge cases. For example, arrays shorter than 3 elements, such as 1, 2, are invalid by definition. Arrays with repeated elements or flat sections, like 2, 2, 2, or 2, 3, 3, 1, fail the conditions for strictly increasing and decreasing slopes. Arrays with the peak at the start or end, such as 3, 2, 1, or 1, 2, 3, are also invalid. On the other hand, arrays that follow the mountain structure, like 1, 3, 2, should return true. By handling these edge cases systematically, we can ensure the algorithm works correctly in all scenarios. The simplicity of the data structures involved, just the input array and the index variable, further contributes to the robustness and clarity of the solution. The final implementation ties everything together. After confirming the minimum length requirement, we use a while loop to find the peak by traversing upward. If the peak is invalid, we immediately return false. A second while loop then verifies the downward slope, ensuring the elements strictly decrease. If we traverse the entire array successfully, the algorithm returns true. Otherwise, it returns false. The time complexity of this solution remains O(n), as we only perform 2 linear traversals of the array. The space complexity is O(1), as no additional data structures are used beyond the input array and the index variable. To further optimize, the upward and downward traversals can be combined into a single loop to reduce redundant checks, though this is not strictly necessary for correctness. Early exits during validation also save computational time in cases where the array fails obvious conditions, such as having the peak at the boundaries. Overall, this algorithm balances clarity, efficiency, and robustness, making it an ideal solution for determining whether an array forms a valid mountain. The provided solution checks whether the given array constitutes a valid mountain array. Here's the detailed explanation. 1. Input validation. The function first checks if the length of the array ARR is less than 3. Since a valid mountain array requires at least 3 elements to have a peak and 2 sides, the function returns false immediately if this condition is not met. 2. Ascending phase. The variable I is initialized to 0. A while loop is used to iterate through the array as long as the next element is greater than the current one, strictly increasing. The index I is increment to move towards the peak. This loop stops when the array starts descending or when the peak is reached. 3. Peak validation. After the ascending phase, the function ensures that the peak is neither the first element, I = 0, nor the last element, I = n1. If the peak is at either of these positions, the function returns false, as a valid mountain must have both an ascending and descending side. For a descending phase, a second while loop is used to check the strictly decreasing part of the array. It continues iterating as long as the next element is smaller than the current one, incrementing I to move down the mountain. 5. Final validation. After both the ascending and descending phases, the function checks if I has reached the last index of the array, I = n1. If this condition is true, the array forms a valid mountain, and the function returns true. Otherwise, it returns false. This implementation ensures that all the requirements for a valid mountain array are met, and it operates in O(n) time complexity, as each element is traversed at most once. Here, we start with the implementation of the valid mountain array problem in Java. First, we define a class name solution and a method valid mountain array that takes an integer array, ARR, as input. Inside the method, the first step is to determine the length of the array and store it in the variable n. A valid mountain array must have at least 3 elements, so we check if n is less than 3. If it is, we return false immediately since the array cannot form a mountain. Next, we initialize a variable I to 0, which will serve as our pointer to traverse the array. The first phase is to ascend the mountain. Using a while loop, we continue moving the pointer I as long as the current element is less than the next one. This represents the climbing process, where the elements are strictly increasing. After this loop, I should ideally point to the peak of the mountain. However, we add a condition to ensure that the peak is neither the first element nor the last element of the array. If I is 0 or equals n1, we return false, as this would mean the array doesn't have a proper peak or descent. Now, we move to the descent phase of the mountain. We use another while loop to continue moving the pointer I as long as the current element is greater than the next one. This simulates descending from the peak, where the elements are strictly decreasing. Once this loop completes, we check if I has reached the last index of the array, which indicates that we successfully traversed both the ascent and descent. If I equals n1, we return true, confirming that the array forms a valid mountain. Otherwise, we return false. This ensures that all the conditions of a valid mountain array are satisfied: a proper ascent, a single peak, and a proper descent. To understand how to determine if an array is a valid mountain array, let's start with example 1, where the input is 1, 3, 2. First, we check the length of the array, which is 3. Since the length is at least 3, we can continue with the process. Next, we begin ascending to the peak. Starting at index 0, we compare ARR 0, which is 1, with ARR 1, which is 3. Since 1 is less than 3, we increment our pointer I to 1. Now, we compare ARR 1, which is 3, with ARR 2, which is 2. This time, 3 is greater than 2, so the ascent stops, and we identify the peak at index 1. We then validate the peak by checking if it is either the first or last index of the array. Since index 1 is neither the first nor the last, we proceed to the descent. During the descent, we compare ARR 1, which is 3, with ARR 2, which is 2. Since 3 is greater than 2, we increment I to 2. Now I equals n1, which means we have reached the end of the array. At this point, we perform a final check. Since the pointer I is equal to n1, the array satisfies the mountain property, and we return true. Now, let's look at example 2, where the input array is 1, 2, 3, 4. Again, we start with an initial check of the array length, which is 4. Since the length is greater than or equal to 3, we move on to the next step. We begin ascending to the peak, starting from index 0. Comparing ARR 0, which is 1, with ARR 1, which is 2, we see that 1 is less than 2, so we increment I to 1. Next, we compare ARR 1, which is 2, with ARR 2, which is 3. Since 2 is less than 3, we increment I to 2. We then compare ARR 2, which is 3, with ARR 3, which is 4. Again, since 3 is less than 4, we increment I to 3. At this point, I equals n1, which means we have reached the end of the array during the ascent. Now, we validate the peak for example 2. Here, we check if I equals n1. Since the peak is the last element of the array, it fails the mountain property. A valid mountain array requires that the peak is neither the first index nor the last index. As a result, we return false. Next, consider example 3, where the input array is 1, 3, 3, 2. Once again, we start with the initial check of the array length, which is 4. Since the length meets the minimum requirement, we proceed. For the ascent, we start at index 0 and compare ARR 0, which is 1, with ARR 1, which is 3. Since 1 is less than 3, we increment I to 1. We then compare ARR 1, which is 3, with ARR 2, which is also 3. Here, 3 is equal to 3, so the ascent stops, and we identify the peak at index 1. Moving on to peak validation, we check if I equals 1 is the first or last index. Since it is neither, we proceed to check the descent. For example 3, we begin descending from the peak. Comparing ARR 1, which is 3, with ARR 2, which is also 3, we see that the values are equal. This violates the condition for a valid descent, where each element must be strictly smaller than the previous one. Since the descent is invalid, the array does not satisfy the mountain property, and we return false. This demonstrates that any plateau, whether during the ascent, at the peak, or during the descent, invalidates the mountain structure. The time complexity of the given solution is O(n), where n is the length of the input array ARR. Let's break this down step by step. First, the initial check to determine if the array has fewer than 3 elements is a simple operation that takes constant time, O(1). Next, as we ascend to the peak of the mountain, the while loop processes elements as long as each element is smaller than the next. In the worst-case scenario, the loop will iterate through all elements up to the peak, which means this step takes O(n) time. Then, to validate the peak, a constant time check ensures that the peak is not the first or last element of the array. This operation, too, is O(1). Now, as we start descending from the peak, the second while loop iterates over the array as long as each element is greater than the next. Similar to the ascent, in the worst case, this loop processes the remaining elements from the peak to the end of the array, which takes O(n) time. Finally, a constant time operation checks whether the entire array has been successfully processed by ensuring the pointer has reached the last index. This check takes only O1. Since the two loops together iterate over the array at most once, and no element is revisited, the total time complexity of the solution is O(n), with all other operations contributing only constant time. The space complexity of the solution is O1, because it uses only a constant amount of additional memory. Let's break this down. First, the input array ARR is provided as an argument, and since we're not making a copy or modifying it, this doesn't contribute to extra space usage. Then, we use a few variables like n to store the length of the array and I as an index pointer. These variables require only constant space, O1. Additionally, the solution avoids using any auxiliary data structures, such as lists, stacks, or queues. Since all operations are performed in place and no extra memory is needed, the overall space complexity remains O1. When comparing approaches, a naive solution might involve explicitly identifying the peak and checking the left and right sides of the array separately. While this could still achieve O(n) time complexity, it involves multiple scans of the array and is more cumbersome to implement. In contrast, the optimized approach presented here simplifies the logic by combining the ascent and descent into a single pass using a pointer. This achieves the same O(n) time complexity but with cleaner, more efficient code. In terms of best, average, and worst cases, the best case occurs when the array is very small or fails a condition early, requiring only O(1) time. In the average and worst cases, we process the entire array once, resulting in O(n) time complexity. From a mathematical perspective, each element in the array is processed at most once during the ascent or descent phases. No element is revisited, ensuring that the maximum total iterations across both loops is n, which confirms the O(n) time complexity. As for space, the algorithm does not allocate any additional memory proportional to the size of the input. All operations are executed using a fixed number of variables, so the space usage remains constant at O1. Together, these factors demonstrate the efficiency of the solution both in terms of time and space. When solving the valid mountain array problem, there are several common mistakes to watch out for. First, not checking the array length is a frequent oversight. Remember, a valid mountain requires at least 3 elements, 1 peak and 2 slopes, so arrays with fewer than 3 elements can never form a mountain. Failing to account for this can lead to errors or unnecessary runtime issues. Next, we have the mistake of allowing non-strict slopes. A valid mountain array must strictly increase before the peak and strictly decrease after. If there are flat segments, or consecutive elements have the same value, the array no longer satisfies the mountain conditions. Another error is misplacing the peak. The peak cannot be at the start or end of the array because it must have an increasing slope before it and a decreasing slope after. Without both slopes, the array fails the mountain criteria. Lastly, stopping after finding the peak is another issue. Some solutions focus only on the increasing part up to the peak and don't verify the entire decreasing phase. This is problematic because a valid mountain requires both strict phases to be checked and validated. Inefficiency in implementation is another frequent pitfall. Using nested loops or recalculating data unnecessarily can result in slower solutions. The valid mountain array problem can be solved in O(n) time with a single traversal, so inefficient approaches may struggle with large inputs. In terms of interview insights, it's important to emphasize the structure of a mountain array, a strict increase to the peak followed by a strict decrease. Edge cases play a big role here, such as arrays with fewer than 3 elements, constant arrays, or arrays where the peak is at the boundary. Recognizing patterns is also key. Problems that involve validating specific array structures often require careful, linear scans with adherence to strict rules. Highlighting your ability to implement a one-pass O(n) solution with O(1) space will demonstrate a strong grasp of efficiency, something interviewers value highly. Lastly, be ready to explain how your solution handles edge cases in detail. This includes scenarios like arrays with only 2 elements, entirely flat arrays, or borderline cases where the peak is misplaced. This problem shares similarities with a few related problems on LeetCode. For instance, LeetCode 852 asks you to find the peak index in a mountain array, which is a simpler version of this problem. LeetCode 845 goes a step further by requiring you to find the length of the longest mountain in an array. Other related problems include LeetCode 162, where you need to identify any peak element in an array, and LeetCode 1095, which involves searching for a target value in a mountain array using binary search. Alternative approaches can also be considered when solving this problem. A dual pointer approach, for example, uses two pointers starting from the left and right to locate the peak and validate the slopes simultaneously. This method avoids redundant checks and maintains O and time and O1 space, although it can be slightly more complex to implement. Another option is binary search for the peak. This approach officially identifies the peak in O log n time, but you still need to validate the slopes on both sides, which brings the total complexity back to O n. While binary search can be useful, a single-pass linear solution is often more intuitive and practical for this problem. Great job! To recap, we verified the conditions for a valid mountain array using a single traversal, achieving an efficient O n time complexity. Remember the importance of handling edge cases and staying mindful of problem constraints. Thank you for watching. Be sure to like and subscribe for more problem-solving content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!